Okay. Last time, actually, we discussed the concepts related to Fourier series and some information related to special function. So we basically go through this Fourier series. And special functions. Okay. So now we move to Fourier transform. Okay. So so for Fourier series, actually, so we have a kind of a periodic function xt. So this is a kind of a periodic function with a period of t. So then we basically have this relationship. So this is the angular frequency of the signal and this is the period of the signal. So we have kind of a random periodic signal. So we apply Fourier series and represent this as a kind of an infinite sum of complex exponentials. So these are the complex exponentials. So these are complex exponentials. Complex exponential. So these are the Fourier series coefficients, Fs coefficients. So this is the periodic random function. So we basically represent any kind of a periodic function as a kind of an infinite sum of these complex exponentials. So if we expand this, so we got this kind of a equation. A1 e to the power j omega naught t, A2 e to the power j 2 omega naught t, okay, and a minus 1 e to the power minus j omega naught t. So like this. So then we claim that, so this is actually the DC component. So the component at frequency of 0. So then this is the frequency of f naught. So this is the coefficient at 2f naught. So this is the coefficient at minus f naught, right? So once we expand this infinite sum, so we have this type of individual terms. So then we claim that this a naught is actually the amplitude at frequency of 0. So this A1 is the contribution from this frequency of F naught. A2 is the frequency of the contribution of this to F naught. A minus 1 is actually the frequency contribution of this minus F naught and so on. So then we came up with this kind of so we'll put F. So then we found that this is actually represent the contribution of 0 frequency. So then we have F naught, 2F naught, 3F naught. So we have this kind of, and minus F naught, minus 2F naught. So we claim that this is the magnitude spectrum of xt. So similarly, we can get the phase spectrum as well, but for the time being, so we'll focus on this magnitude spectrum. So actually, then we can give a kind of a hint about the individual frequency component affecting to this xt, or else we can say that so this xt, which is our random periodic signal, is a kind of a composition of the set of frequencies. For example, if we have here 4f0 and the amplitude is 0, we can simply say that there isn't any frequency component at 4f0. So then we know that this xt doesn't have any frequency component at 4f0. So no any impact on 4f0 to xt. So likewise, depending on the magnitudes of these individual Fourier series coefficients, we can simply give a kind of a hint about the frequency distribution of xt. So what are the frequency component that impact to xt? Or so what are the frequency component which generate this xt? So from this one, so for example, if we stick into this and we'll assume that rest of the frequency components are 0. So we can simply claim that x naught is actually comprised of 0 frequency plus or minus f naught frequency and plus or minus 2f naught frequency and plus or minus 3f naught frequency, like that. So by converting xt into Fourier series, so we can basically give a kind of a clue about the frequency component which is inside this xt, or what frequency component contributes to xt. So then, so this is actually, this A case are actually in frequency domain. So I believe like you can capture that, or you can identify this. The Fourier series coefficients are the contribution of each and every frequency component. So once you draw the magnitude spectrum, we can simply identify those. So this is the magnitude spectrum. So by looking at this magnitude spectrum, we can say that so the contribution of 0 frequency is A naught. So contribution of F naught frequency is A1, 2F naught is A2, 3F naught is A3, likewise. So this Fourier series coefficients are giving the exact actual contribution of this individual frequency. So then we can claim that A case basically represent the frequency domain effects. So AK basically is the frequency domain effect. So this is actually in time domain. So this is time domain signal. So this is time domain signal. And once you evaluate this Fourier series, we can simply identify this A case is the frequency domain contribution. So then, so we can basically claim that xt is in time domain and AK is in frequency domain. Okay. Again, like to evaluate AK, so initially during the signal and system one, we got a kind of equation like this. So this xt e to the power minus jk omega naught t dt. So if it is xt is mathematically defined. So if you know the function of xt, whether it's a sine omega t or cos omega t or t squared plus 2t, like, so if you know, or if you define xt in a mathematically, so you can easily evaluate this integral and find out this individual Fourier series coefficients. So these are the two equations we basically focus during last module. So if you want to apply Fourier series, so this is the equation. So if we can simply say it, like any kind of a periodic random signal can be converted into infinite sum of complex exponentials. So this in the prefactor of this complex exponential. So these are the prefactors or the coefficients of the exponential functions basically give the frequent contribution of this each and every frequency component. So we can evaluate this contribution or the Fourier series coefficient by integrating this original time domain function and the product of these two, original time domain function and e to the power minus jk omega naught t over a period, because this is a periodic function. Okay, so this is the Fourier series basically. So now we move to the Fourier transform. So now we move to the Fourier transform. So what happens? So let's take a kind of a substitution. So we take a kind of a substitution, omega equals k omega naught. Okay. So this is a substitution, and we actually try to figure out what happens to the system when t goes to infinity. So we basically identify kind of a substitution. So omega equals k omega naught, and so we'll try to figure out what happens to the ultimate equations and the functions when t goes to infinity. So let's think about a very simple function. So we have this kind of a function. So this is your xt. So let's assume this is kind of periodic. So this is t by 2. This is minus t by 2. This should be t1 minus. This is plus t1. So this is a kind of a periodic square pulse having a period of t. So what happens actually when this t goes to infinity? So what happens if this t goes to infinity? So t is the period of the function. Can someone tell me, like, if this t, the period of the function goes to infinity, what happens to this xt? So we basically consider a periodic signal having a period of t. So now we let this t to moves to or goes to infinity. So what happens to xt? So let's see this. So we have this kind of a function. So once this t goes to infinity, So it means this periodic function converge to this kind of a pulse. So initially we consider a kind of a periodic function xt having a period of t, and then we let the period to be infinity. So then basically, so this block moves to infinity and this block moves to minus infinity. So then you can basically extract the one pulse of this periodic function. So we basically extract this one by letting this period goes to infinity. So this is the block. So then, so it means, so by letting this t to be at infinity, so this periodic waveform wave convert into a kind of a pulse. So now this is a kind of a pulse. So this is the simple impact when you let the period of the function to be at infinity. Okay, so then we have these two equations xt, so comes from this Fourier series expansion. Okay, so then we claim that this is a time domain quantity, xt is the time domain quantity, and this is the frequency domain quantity. So then what happens if t goes to infinity? What happens to this omega, which is defined as k omega naught? So k, this omega naught is the actually omega naught equals to 2 pi over t. So this is the period of the signal, and omega naught is the angular frequency of the signal. So then once t goes to infinity, so when t goes to infinity, so we know that omega naught also goes to 0. So it means once you let your period to be at infinity, the angular frequency of the signal is simply converging to 0, or the value of this omega naught becoming smaller and smaller. So this k is actually an integer. So k is an integer. So we know that k actually takes values like 0, plus or minus 1, plus or minus 2, plus or minus 3. So likewise, you can take any value in between minus infinity to plus infinity for this particular k. So this is actually converged to 0. So then what happens to this omega? So k is an integer, omega is the angular frequency of the signal, and by letting this t goes to infinity, we found that the angular frequency of the signal becoming smaller and smaller. So then what happens to this omega, which is equals to k omega naught? So we'll try to understand it through a kind of a graph or kind of a figure. So we can illustrate this graphically. So this is your k equals 0, this is k equals 1, k equals 2, k equals 3, k equals 4, and so on. So we have this, let's assume we have, so this is omega x 0, this is omega naught, This is 2 omega naught, 3 omega naught, 4 omega naught. So this is k omega naught axis, this is k. Okay. So this is, let's assume like I am just explaining this k omega naught. So we have this k, it's a kind of integer, can take any values from minus infinity to plus infinity, and omega naught is a kind of a constant which is basically come from the period of this signal. But we know that once we let the period of the signal to be at infinity, so we know that the value of omega naught is becoming smaller and smaller. So for the time being, assume that this is the omega naught. So this distance represent the omega. So this is 0, this is omega naught, this is 2 omega naught, 3 omega naught, 4 omega naught, and so on. So once we let this t to be infinity, we know that omega naught should be smaller and smaller. So then k omega naught actually again becoming smaller and smaller. So once you reduce your omega naught, so then after reducing this omega naught with respect to the previous one, this omega naught would be appear here. So then the 2 omega naught would be appear here. 3 omega naught here, 4 omega naught, 5 like that. So then what happens to this? So then we basically have the samples which are very close, because the omega naught goes to 0, so the value of omega naught becoming smaller and smaller. So the end of the day, so the samples are basically having 0 gaps. So initially we have this much of gap between 0 omega naught to omega naught and 2 omega naught, because this gap represents the omega naught. So once you let this omega naught to be 0, it means the gap between these consecutive samples becoming smaller and smaller. So ultimately, once your period goes to infinity, your omega naught reaches to 0. So then actually this omega becomes a continuous variable. So initially this k omega naught is a kind of a discrete variable, because omega naught has a certain magnitude, certain value, which basically come from the period of the signal, which is not a kind of infinite at that time. So the k omega naught gives a kind of a discrete set of values. So these are the discrete set. So this is 0, this is omega naught, this is 2 omega naught, 3 omega naught, 4 omega naught. So k omega naught is initially becomes a kind of a discrete variable. So once you let this t period of the signal to be infinity, so then omega naught becomes smaller and smaller, or it's basically converged to 0. And whether this k omega naught, the product of k and omega naught is a discrete variable, ultimately this omega converge to a kind of a continuous variable, because we found that once you reduce the value of this omega naught and let it to be 0, so the distance between the consecutive samples are getting smaller and smaller. So then ultimately the consecutive samples may be like overlapping. So then this discrete variable basically converts into continuous variable. So this is what happens when t goes to infinity. So your discrete variable convert to a kind of a continuous variable. So then what happens, like previously we have magnitude spectrums like this: 0, omega naught, 2 omega naught, minus omega naught, minus 2, a0, a1, a2, minus a minus 1, a minus 2. So this is the discrete plot. So this is a discrete plot. This is the magnitude spectrum, and it's a discrete plot. So once we let this t to be infinity, so we know that these omega nodes actually converge to 0. So then this sample moves to this, and 2 omega naught also close to 0. Likewise, all these samples are simply overlapping. So then this discrete plot converts to a kind of a continuous plot. So then discrete plot converts to a continuous plot. So hope it's clear. So when this t goes to infinity, omega naught goes to 0. So then k omega naught is very, very small. So then omega becomes a kind of a continuous variable. Omega equals k omega naught. So then once you let that period to be infinity, ultimately this periodic function converge to a kind of a pulse. So this periodic function, periodic waveform converts to a pulse, and discrete plots. So whatever the magnitude and phase spectrums which are in discrete domain convert to continuous plots. So it means like this. So initially you have this kind of a spectrum. Now it would be like this. So initially you have this kind of a phase spectrum. So now it would be like this. So whatever the discrete spectrums simply moves to kind of a continuous spectrums. So then the discrete spectrums converge to continuous spectrums. And so what happens to this AK? What happens to this AK? So we'll just multiply T. So it's like this xt e to the power minus j omega naught k t. Okay. So now this period goes to infinity. So then for this case, actually we can integrate this like from minus t1 to plus t, or minus t by 2 to plus t by 2. But once this t goes to infinity, so this integral would be, minus infinity to plus infinity. Because this t by 2 moves to plus infinity, and this minus t by 2 moves to minus infinity. So then if you simply integrate it over the period, now this period would be finite. So then the lower and upper limit of the integral would be minus infinity and plus infinity. So x is there. What happens to this quantity? K omega naught. So with this substitution, we can simply claim that, so this becomes omega. So now our definition is actually this. So we can simply claim that. So TAK is denoted by this. So we'll explain it later. So this is minus infinity to plus infinity xt e to the power minus j omega t dt. So this k omega naught becomes a continuous variable omega, and tak is actually. So this again represent, this is the, so previously we define it as a kind of a Fourier series coefficients. But now we define this quantity. So we'll use this capital X within bracket j omega. So j basically represent the complex domain, omega represent this frequency domain in continuous mode, x basically represent the Fourier transform. So the Fourier transform is capital X. So for this case, if your signal is xt, Fourier transform is basically capital X. Now this time domain quantity is simply represented by simple or small x, and the domain is represented by this t time. So once you convert it to frequency domain, it becomes capital X within bracket j omega. So you can simply put x within bracket omega or j omega. Doesn't matter. So both would be fine. X omega or x j omega. So this is the Fourier transform of xt, and how do you evaluate the Fourier transform? Just take the product of xt and e to the power minus j omega t. So this is your continuous variable, and integrate over the infinite domain, minus infinity to plus infinity. So once you integrate this with respect to t, so this is a time domain function. We just multiply it with this exponential, complex exponential. So once you multiply it with complex exponential, ideally your result will be a kind of a complex function. So that's why we put j here. So then if you integrate it out over the t variable, so whatever the output of this integral would be a function of omega, because we basically integrate it with respect to t and substitute plus infinity and minus infinity instead of t. So then you don't see any t variable once you complete this or evaluate this integral. So the only variable which appear in the output is omega. So that's why we put omega. So this output would be in a domain of omega. And we know that this real quantity, if you multiply a real quantity with a kind of a complex exponential, so ultimately the results would be a kind of a complex function. So that's why we put j here. So x within bracket j omega gives the Fourier transform of xt. So for example, if you have st, and the Fourier transform would be as j omega. If you have zt, simple zt, your Fourier transform would be capital Z j omega. If you have ht, the Fourier transform would be capital H j omega. So likewise, so you can simply denote the Fourier transform by just use the capital letter, and within bracket you can put j omega, because the output would be a kind of a complex one. That's why we put j, and once you integrate it over a time, so the function would be ideally in omega. So then so Fourier transform, so if you have xt, the Fourier transform of xt is xj omega equals minus infinity to plus infinity xt e to the power minus j omega t dt. So this is the Fourier transform. So similarly, you can obtain the inverse Fourier transform as well. Inverse Fourier transform. So inverse Fourier transform means the expression, or this is the inverse. So the Fourier transform is basically in omega. So inverse Fourier transform is actually xt. So xt is actually 1 over 2 phi minus infinity plus infinity. Here you have xj omega e to the power j omega t omega. Okay. So this inverse is in t. So keep in mind, if you want to evaluate the Fourier transform, this is actually in frequency domain. So this is in frequency domain. So that's why we have omega here. So then you have to take the time domain function and multiply it with e to the power j minus j omega t and integrate it over with respect to t. So then only you have this output in as a function of omega. So this is inverse Fourier transform. Inverse Fourier transform. So ultimately you'll get a time domain function. So this is xt. So it's 1 over 2 phi integral minus infinity. Here you have to put the frequency domain function. To obtain a frequency domain function, you have to integrate a time domain quantity. To obtain a time domain quantity, you have to integrate a frequency. So we'll put the Fourier transform. This is your Fourier transform. And we multiply e to the power j omega t. And to obtain expression in t, you have to integrate it out with respect to omega. So keep in mind the difference. So this is the simple expressions for this is your Fourier transform. This is your inverse Fourier transform. So Fourier transform, we basically convert t to f, time domain quantity to frequency domain. So you have xt and we convert it to x j omega. In inverse Fourier transform IFT, so you have frequency domain quantity and convert it to time domain. So you basically convert x j omega to xt. Okay. So these two expressions you have to anyhow remember it, but so this time again I feel like we have to move with this online exam, so then no point of wasting your memory, so you can just pick it from whatever the lecture. So this is either given in the question or you can simply pick it from your lecture note or whatever the material. So no need to memorize this. So this is your Fourier transform. This is your inverse Fourier transform. If you want to evaluate the Fourier transform, just evaluate this integral. So if you want to get the inverse Fourier transform, then it means like you should aware or you should be uh, known to this Fourier transform of this function. Then only you can get the inverse Fourier transform. So I believe like this briefing would be. Give a kind of a clear idea about what is Fourier series and how do we map this Fourier transform with Fourier series, what happens. So when we move from Fourier series to Fourier transform by letting the period to infinity. So then as a summary, so whatever the discrete spectrums convert into continuous spectrum. Okay, so this is the major difference. So Fourier series, you have discrete spectrums. If you have Fourier transform, you have continuous spectrums. So this is the major difference if you are dealing with continuous time signals. So if you apply Fourier series, you will end up with a kind of a discrete spectrum. So if you apply Fourier transform, you basically get the continuous spectrums. Okay. So hope so you have this slide set which I shared previously. So in slide number 3, so Fourier series to Fourier transform. So you can clearly explain that the stuff which we discuss here. So we have a kind of a periodic pulse, and once you apply Fourier transform, this periodic signal would be converted into a kind of a pulse, and this discrete spectrum is basically converted into a kind of a continuous spectrum. Again, like the next thing is actually so we know that if it is a discrete signal, so let's see, this is a this is a kind of a periodic signal. So once we let this t to be at infinity, so we basically get this path. So then actually this, if assume that this is x tilde t and this is xt, so we can simply claim that x tilde t is equals to xt when t less than or equals to t by 2. So let's assume this is t by 2. So if you just consider the fundamental period, so if you just capture this fundamental period, so you can simply claim that x tilde t and xt is equals during this fundamental block. So from that, we can simply obtain a relationship between the Fourier series coefficients and the Fourier transform. So now, so we have periodic function x tilde. And for this periodic function, we can easily evaluate Fourier series coefficients. So these are Fourier series coefficients. And we have this xt. So we can get this Fourier transform for this path xj. So then we can have a kind of a relationship between these two quantities. AK, so which are the Fourier series coefficients of the periodic function, and xj omega is the pulse which we simply get it from this periodic function by letting the period to be infinite. So this is your periodic function. So this is your periodic function. And these are the Fourier series coefficients. This is the pulse we obtained from this periodic function by letting the period to be infinite. So if it is the case, so we can simply obtain this relationship. So AK, the Fourier series coefficients of the periodic function which is generated from this basic shape can be obtained by this expression. So if we take a small example, so let's think of this. So we have triangular form. So this is UXT. So you can generate a kind of a periodic function from this basic shape or basic pulse. So this is the pulse. So you can simply generate a periodic function using this basic shape. So it would be something like that. So you can simply repeat it again and again and develop a kind of function. So this is the periodic function which we basically derive from this pulse or this basic shape. So then this would be the x tilde according to the previous version. So we can obtain the Fourier series coefficients for this, and we can obtain the Fourier transform for this. So if you are given this, you can just apply Fourier transform and obtain this. And if you are known this function, you can apply Fourier series and get the values of Fourier series coefficients. So if you know this one, you can basically get the Fourier series coefficient for a function x tilde, which is basically generated or derived from this fundamental pass. Okay, so for example, we'll take one more example. So we have this kind of. So here you can generate this kind. So this is your xt. So this is your x tilde. So see, so this is the pulse. So this is your pulse. And you can easily evaluate the Fourier transform by applying the previous equations. So here you have x tilde, which is actually derived from this shape. So we basically derive it from this shape. So we just put this basic one repeatedly or periodically to obtain this periodic function xt. So then we have x tilde t, which is actually generated from xt. And you can take AK by applying Fourier series. So then if you want to evaluate this AK, you can just take this, the period of the signal and the so it means like 1 over T X J K omega. So how do you get it? So we know that this is a continuous function. This is a continuous function. So let's assume like this. So this is a continuous function x j omega. So we can just sample it at this omega naught rate. So we can sample it. So this would be omega naught. So here the second sample would be 2 times omega naught. So this third sample would be 3 times omega naught. Then 4 times omega naught likewise. So then these are the, so this is omega 0. So this is the first, this is A0, this is A1, so this is A2, this is A3, this is A4, and so on. So if you know the Fourier transform, so we can easily get the Fourier series coefficient of a periodic function which is derived from this xt. So keep in mind, so you can obtain the Fourier series coefficient of a function if you know the Fourier transform of this, and this AKSR actually belongs to the function which basically derived from this. So if you know this kind, the Fourier transform of this, you cannot obtain the Fourier transform of this kind of function. Fourier series coefficient. So if you know this x j omega, so you cannot find AKs directly. Maybe there may be a kind of a mechanism to map this by using Fourier transform properties and so on. But you can't directly obtain this Fourier series coefficients using this equation. So our argument is, if you want to evaluate a Fourier series coefficient of a given kind of a periodic function, so this periodic function should be generated by this. Otherwise, you can't apply this equation. So you can get this Fourier series coefficients by applying different Fourier series properties, but you cannot get the Fourier series coefficients of this function, because this periodic function is basically not generated from this. So if it is generated from this basic pulse, then only you can get the Fourier series coefficients immediately by applying this. So how do you apply is this? So x j omega is a kind of a continuous function. You basically discretize it or sample it from the rate of omega naught. So then you can basically pick the Fourier series coefficients of that function. So next we'll try to discuss one simple example. So this is the exercise given in your paper. So xt is defined like this. So xt is 1 for mod t less than t1, 0 otherwise. So this is illustrate this way. So this is your xt, this is t1, this is minus t. So you are asked to evaluate the Fourier transform. So you asked to evaluate the Fourier transform. So how do you evaluate the Fourier transform? So this is the fundamental equation xj omega equals minus infinity plus infinity xt e to the power. So this is the equation. So you can get it from anywhere else. Okay. So we'll try to get the Fourier transform. Okay. So once you integrate it from minus infinity to plus infinity, this xt, we know that this function is only defined in between minus t1 and plus t1. So you can truncate this integral to this minus t1 to plus t1. So the from minus infinity to minus t1, so the functional value is 0. Similarly, from t1 to plus infinity, again the functional value is 0. So in between these limits minus t1 and t1, so your functional value is 1. So this xt would be then 1. So this is actually 1 e to the power minus j omega t dt. So we'll do the substitution. So e to the power minus j omega t divided by minus j omega and minus t1 plus t. So we have e to the power j omega t1 minus j omega t1 j omega. So we know that this relationship, so we discuss it. Sine theta actually e to the power j theta minus e to the power minus j theta divided by 2j. So we can apply this here. We can, so we have to make this argument inside. So omega is there, so we have to put, so we have to put 2 here. So we'll put 2 here and so then this becomes 2 over omega. Here you have sine omega t1. Okay. So this 2j can be simply accommodated to this. So this 2j. Sorry, this quantity minus this quantity divided by 2j can be replaced with sine omega t1. So then we have 2 and this omega here. So then we can further simplify it. So we know that if you have a sine function, so we can use this sinc. So we know that sinc x equals sine x divided by x. So we can use that as well to simplify it further. Okay, so you have 2 omega sine omega t1. So we have omega here. So we have omega here. So in addition, we need to put t1 here to make it sinc function. So to remove this t1, we have to add t1 here. So then 2 t1. So this becomes sinc. So then this is sinc omega t1. Okay. So now the Fourier transform is actually xj omega equals 2t1 sinc omega t1. So this is a continuous function because omega is a kind of a continuous signal. So this is continuous variable. So then this becomes a continuous spectrum. T1 is a kind of a constant. So how do you plot this one? So we ended up with this xj omega equals 2t1 sinc omega t1. Okay, so we know that the sinc function is something like that. So this is sinc function. Okay, so what's the value of this one? So at at this 0 point, so the sinc function would be 1. So then this becomes 2 times t1. So this. So what about these values? So we argue like that this is equals to sine x of x. So then the 0 crossing point would be omega t1 would be n times 5. So then this is your omega axis. So then we can simply claim that omega equals n phi over t1. So then this first point would be phi over t1. So this is 2 phi over t1. So this is 3 phi over t1. So this is minus phi over t1. This is minus 2 phi over t1. This is minus 3 phi over t1. So these are the 0 percent points. So in between those values, your function is continuous. So this is continuous. So previously we obtained a kind of a discrete function. Now it's a continuous function. So previously we have a case. So each and every k value we have a kind of a discrete path, discrete stem. But in this case, omega is a continuous function. Omega is a continuous function. You will end up with a kind of a continuous spectrum. So this is your Fourier transform magnitude spectrum. So then, so this is the pulse which we refer here. So let's assume, so we have x tilde t, which is derived from xt with a period of t. Less than. So let's assume we have a kind of a periodic function x tilde t, which is basically derived from say xt, this pulse, with a period of t. So then what is the derived function? So this is the derived function. So this is the derived function x tilde t. Okay. So if you want to evaluate the Fourier series coefficient for this x tilde, so we can easily get these Fourier series coefficients by applying this. So we know the Fourier transform of this basic law. So it's given here. So if you just discretize or sample it from the period of omega naught, you can get the Fourier series coefficient. So we'll put this. So the period is t, x j omega is actually 2t1 sine. So instead of omega, you can replace k omega naught. So k omega naught t. So if you remember the previous example we discussed, so we get the same function. So if you remember the discussions we had previously, it's similar. So you can just refer the Fourier series, and we discuss the evaluation of Fourier series coefficient with this type of a periodic function. Now we basically get it through this Fourier transform of this x. So then AKs are actually equals to 2t1 over t sinc k omega naught t1. So then actually by sampling these omega naught, the frequency of omega naught, so we can get it simply. So maybe you can take one sample here, another sample here, another sample here, sample here, likewise depending on these values omega naught and t1. So you can easily get the discrete version of this continuous signal by picking the relevant sample. So then this would be like a discrete signal. So this is the Fourier series of this x tilde. So this is the Fourier transform of xt. Okay, so we'll take another example. So the exercise 2 in the slide set, EX. So here it's given that the signal xt is equals to e to the power minus, e to the power minus at ut, where a is greater than 0. So by looking at this one, we know that if a is greater than 0 and if you have minus sign here, so we can simply claim that this is a real exponential function, exp function, having this kind of a trend, decaying. It's a decaying function because you have a negative exponent. And with this ut, so you know that this is basically defined for t greater than or equals 0. Because ut is only defined for t greater than or equals 0. So ut is actually 1 for t greater than or equal to 0. So the otherwise it's 0. So ut is something like that. So from here to here, functional value is 0. From here to here, functional value is 1. So then ultimately we'll get this kind of a function which is defined only for the t greater than 0 scenario. So then we'll apply the basic equation xj omega equals minus infinity to plus infinity xt e to the power minus j omega t dt. Okay, so we know that this xt is basically defined only for t greater than or 0 due to this unit step. So then this integral would be 0 to infinity, xt becomes e to the power minus at. So then we have j omega t dt. Okay, so then we can combine these two exponentials together. So you have 0 to infinity, e to the power minus. So we have a plus j omega t dt. So we can integrate it out. So it's become e to the power minus a plus j omega t divided by minus a plus j omega, and we need to substitute this. So this becomes, so this t infinity means you have 0. So we'll ended up with 1 over a plus j omega. So this is the Fourier transform of this given function, 1 over a plus j omega. So see, so previously we argued that once you introduce this complex exponential, the result would be a complex function. See this complex quantities there. And once you integrate it over the t, and whatever the t values in random quantities in the expression would be simply vanished, and so the ultimately we'll get this the function of omega. So see, so this is the constant. So then by looking at this, so now we have x j omega. It's a complex function a plus j omega. So by looking at this, we can generate two quantities. One is the magnitude spectrum. So the other one is phase spectrum angle. So how do you get the magnitude? So this is a complex function. How do you get the magnitude? So the magnitude equals 1 over the square root of sum of the squares. So this is your magnitude. And what about the phase? So it's like minus tan inverse. So this is the sine component. This is the cos component. So how do you get it? So if you want to further clarify, so you can convert this into a kind of a polar version. So how do you make it to the polar version? So this becomes square root of a squared plus omega squared, and the angle theta. So the theta would be, so this is cos theta plus j sine theta. So this is tan inverse omega over a. So once you bring this theta to the numerator, so it becomes minus. So this is the magnitude spectrum, and this is the phase spectrum. So you can just plot it as it is. So the magnitude and phase spectrums are simply illustrated in this slide. So I don't try to draw it. So you can just refer those. But end of the day, you can simply claim that this is a continuous function, continuous spectrum. This is phase also again a continuous function. So if it is a Fourier series, we'll ended up with discrete magnitude spectrum and discrete phase spectrum. But if it is a Fourier transform, you basically ended up with continuous magnitude and phase spectrum. Okay, next time we'll discuss couple of properties of this Fourier transform. So any questions so far? Okay, so do you have any questions? So if you don't have, so I'll upload this video, and if you have any questions once you are referring this, so you can just drop it to the discussion forum or send it as email. Okay, so I'll wind up the sessions for the today. So thank you.
Thank you, sir.